Paper is not white. Say that out loud. It sounds insane. Paper comes from trees, and trees are brown. The wood fibers inside are nearly colorless. Somehow the finished sheet ends up brighter than fresh snow. The easy explanation is bleach. Trees are brown, bleach makes things white. Mystery solved. Except bleach doesn't make paper white. A tree is built from two main ingredients: cellulose, long sugar chain fibers that give wood its strength, and lignin, a polymer glue that holds those fibers together and gives wood its brown or yellow tint. In 1879, a chemist named Karl Dahl and Danzig developed the Kraft process, a chemical method for stripping lignin out of wood pulp. That process didn't paint anything white. It just removed the part causing the color. Once the lignin is gone, you're left with pure cellulose fiber. And cellulose barely absorbs visible light at all. Under a microscope, a single fiber looks like a flattened, see-through ribbon, not a white thread. Nearly transparent glass. So how do billions of transparent fibers become a blinding white page? Because paper is spectacularly bad at letting light travel in a straight line. Every fiber sits at a slightly different angle, separated by microscopic air gaps. Light entering paper doesn't pass through one smooth material. It slams into thousands of tiny boundaries, bending and bouncing at each one. In 1908, physicist Gustav Mie worked out the math for exactly this kind of scattering, describing how particles close in size to a light wave scatter it in every direction at once. Cellulose fibers aren't spheres, but the same physics applies. A beam of sunlight crossing one sheet of printer paper can hit thousands of these tiny interfaces before it escapes the other side. Your eyes never receive the original beam. They receive scattered light bouncing back from every direction, all wavelengths mixed together in roughly equal amounts. Your brain has a name for that mix: white. Paper isn't glowing, and it isn't painted. It's just refusing to let any color win. Paper manufacturers actually exploit this on purpose. Premium magazine stock and glossy brochures are coated in microscopic mineral particles, usually kaolin clay or calcium carbonate, sized close to the wavelength of visible light. Those particles aren't there as white pigment. They're there purely to create more scattering surfaces. Brightness itself is a measured industry standard, tested using a diffuse reflectance scan at 457 nanometers under the TAPI and ISO brightness scales. The whitest sheet on the shelf isn't the purest one. It's the one engineered with the most microscopic chaos packed inside it. Here's where it gets stranger. Take a single cellulose fiber and dunk it in a liquid whose refractive index nearly matches cellulose itself. This is a real technique microscopists use, borrowed from immersion oil optics. The fiber almost disappears. Kill the mismatch between materials and you kill the scattering along with it. Nothing about the fiber's actual color changed. Only the boundaries did. Which means the real villain in this story was never cellulose, or bleach or pigment, it's boundaries. Every crossing between air and fiber is another chance for light to scatter, and a single sheet less than 1/10 of a millimeter thick packs in an absurd number of those crossings. This is also why old books and newspapers turn yellow. Cellulose is chemically stable, but leftover lignin isn't. Oxygen and UV light slowly break lignin down, forming new molecules called chromophores that absorb blue light far more aggressively than lignin did originally. Newsprint is especially vulnerable, since mechanical pulping leaves roughly 90% of the original lignin intact to keep costs down. That's fine if the page only needs to survive until tomorrow. Crack open a newspaper from the 1950s and you'll usually find pages already brittle and yellowed. The brown part of the tree simply came back to finish the job decades later. Frosted glass runs on the exact same mechanism. Ordinary window glass stays transparent because it's uniform all the way through, giving light almost no boundaries to cross. Sandblast the surface and suddenly there are boundaries everywhere. The image disappears. The brightness survives. Paper just takes that same trick and applies it through the entire thickness of the material, not only the surface. And once you notice the pattern, it shows up everywhere. Clouds aren't white because water is white. A single droplet is transparent. Pack billions of them together, and they scatter sunlight back and forth until the whole cloud reads as blank white. Snow works the same way. A block of clear ice can be shockingly see-through. Crush it into billions of tiny crystals, and it turns brilliantly white for the exact same optical reason as your printer paper. Which means paper was never the exception to some rule about color. It might be the easiest possible example of the rule. We assume transparency just means letting light through. It doesn't. Transparency means letting light keep its sense of direction. Glass keeps that story intact. Paper shreds it into microscopic confetti, one fiber at a time. So the next sheet you pick up isn't a white object at all. It's millions of transparent fibers, glued together with just enough air gaps to destroy every beam of light that dares to enter in a straight line. Paper isn't white. It's just really, really good at making transparent things disappear.